time for yet another requested revision video. Was asked about limiting reagents. Really, that is just when you do a reaction, unless you've got exactly the same amount of the chemicals that you have in the equation in terms of how much you need to react with how much, one of them will be in excess and there'll be too much of it and it will get left over, and one of them will completely run out. The one that completely runs out is the limiting reagent, so it limits how far the reaction goes. So in this straightforward simple example, which you don't need to consider balancing numbers because you're only talking about reactants when you do limiting reagents. These here, both of them, no balancing numbers, so they're 1 to 1. It will be the same if it were 2 to 2 as well, provided the number is the same. So when you look at that, it's very straightforward. 0.5 of that, 0.4 of that. There's more hydrogen, so simple as that. Now obviously that's kind of almost trivial because it's so simple, but that's the idea, is you work out in the same units, whichever unit you choose, depends what you're doing I suppose, but you work them out in the same units, include considerations of balancing numbers, and then you'll be able to tell which one will deplete to completely zero. That's not right, completely deplete to zero, that's better. And which one will therefore still have some left that you can't get rid of. That is the idea of limiting reagents. Now there's a sort of a thing that people find generally they find it quite difficult, which is odd really, because it's one of the early laws of chemistry, is Avogadro's law, which is when you have gas reactions, and this was a long time ago this was worked out, when you have gas reactions, the chemicals react in volume ratios like they are in the equation. So if you were to do this is 1 to 1, it seems obvious that, oh, there's more hydrogen, but that is actually followed on from the reacting volumes law that is Avogadro's law. So that says that there is more hydrogen than there is chlorine in this example, so that's the limiting, and this one is the one in excess. Now you again would have to consider the balancing numbers when you do this reacting volumes. But when you do that, what is it a function of? Well, at the time when Avogadro's law came about, Avogadro was doing whatever Avogadro was doing with things, in what he was doing, because it was a long time ago, the 1700s. This wasn't a thing that people knew about. But now we have PV equals nRT, the ideal gas equation, and there's a link between pressure, volume, moles, gas constant and temperature in Kelvin. And that, when the conditions don't change, which is critical for doing things with Avogadro's law, so everything is the same temperature and pressure all the way through, the volumes react in the ratio of the equation, which in this case is 1 to 1. So that allows, because of what we now know, and the reason for this being the same for every gas is, of course, gases are almost entirely vacuum, not many particles of mass per centimetre cubed or whatever. So you can have it in those two ways, either looking at moles or we look at volumes, because these are mole equivalent under equal conditions. I'm going to do a few examples on the board, and there's an accompanying sheet for you to practice on. I just need to get the board ready for a number of examples. So there'll be some edits, I'll see you in a moment. So, an example, this time got a balancing number, so that needs to be included in your thoughts. So there's the balanced equation. You obviously need a balanced equation. I've left the state symbols off because they play no role in this example. So the setup of this example, 0.2 moles of methane, 0.3 moles of oxygen. Maybe you could just look at that and go, oh, I can see straight away which one is the limiting reagent. Great. But it allows us to go through the process you need to do when you check the whole, which is the limiting reagent out. Now, one of the things you can do is you can focus on whichever reactant you like. In here there are 2 reactants. I don't want to get involved in 3 and 4 reactants. It makes the question unwieldy. So, but the process will be the same. So, 2 possible ways to do it. You can focus on the CH4, the methane, or focus on the oxygen. In the end, the answer comes out the same, because otherwise it wouldn't be a reasonable thing to do. So, if we focus on the methane, 0.2 moles of methane. Now, when you look at that, looking at the balance of the equation, 0.2 moles of methane would need 0.4 moles of oxygen. Now, you've only got 0.3. So you haven't got 0.4 moles of oxygen, so therefore the oxygen at 0.3 will run out before the methane has all reacted. So the oxygen is limiting. If you focus on the oxygen, the whole thing can be done the other way. 0.3 moles of oxygen, which is what it says you've got in the question, you go, how much would it need? Well, 0.3 moles of oxygen would need half the number of moles, so it's 0.15 moles of methane. You've got 0.2 moles of methane, so you've got more methane than you need to get rid of all of that oxygen, so the methane is in excess and the O2 is limiting. So the process is get a balanced equation, get equal unit quantities, same unit quantities of the reactants, use the balancing number in the judgment of how much of one will be able to react with another. So focus on one, then compare it to the other, make a comparison and then make a judgment as to which one is going to run out completely, which one is still going to have some left over. The one that runs out completely is the limiting reagent. So that's, again, almost a trivial example, because you could look at that and go, oh, it should have been 0.4, it's only 0.3, done. Yeah, that's the same process as that, but done really quickly in your head. When it gets a little more complex, when you've got solutions and volumes, you do have to go through a calculation. I'm just about to do some of those, so I'll see you in a moment. So now we've got a marginally more complicated example. It's written up there, 10.01 grams of calcium carbonate. It's like a lump of marble. Reacted with 50 centimetres of 2 moles per cubic decimetre hydrochloric acid. Need to balance the equation, because it's got balancing numbers in it. There's a 2 in front of the HCl. And we need to know how many moles, and it turns out there's 0.1 of each. So you need the formula mass, because it's a solid and we're adding a solid, we need to know the formula mass. Turns out the formula mass of calcium carbonate is 100.1. And so that's 0.1, but that's 0.1. Same number of moles of each, but of course the balancing number means that one of them is going to run out because of them not going to be reacting 1 mole to 1 mole. So when you look at that there, now you can, like I said, you can do it in one of 2 ways. You can look at either of the chemicals. So if we took it through the calcium carbonate, 0.1 moles of calcium carbonate, balancing number 2 in front of the HCl, it would need 0.2. There's only 0.1. That's limiting. Or you could do it the other way. 0.1 moles of HCl, it would only need 0.05 moles of calcium carbonate to react it all the way. There's more than that, so this is going to run out and it's going to leave some calcium carbonate left over, 0.05 moles left over if you all win. That's kind of it, really. So we'll do some more, and eventually you go and have a go with the accompanying sheet, which has got the answers with it as well. Make sure you're up to speed with it. I'll see you in a moment when we'll do some more examples. Okay, so introduce a couple of other facets of how you have to bring in all your chemical knowledge about calculating moles. 455 cubic centimetres of chlorine gas at a pair of values there of pressure and temperature, and it reacts with a volume of a concentration of potassium bromide. So you need to work out the number of moles from the solution there and the number of moles of gas, of chlorine gas. So moles of chlorine gas using PV equals nRT. You always get given the value of R. It's in your data booklet for your exams. It's just that when you do this enough you remember it's 8.314, even if you don't remember the units. So the number of moles, pressure there, times 455, catch, got to be in metre cube. A lot of people make that slip up, they don't do the, oh, must be in metre cube. So 455 centimetre cubed will be times 10 to the minus 6 in terms of metres cubed. I've written metre cubed there to remind you. Divide by R and divide by the temperature, comes out as 0.1826. Number of moles of KBr, standard, how many moles in a volume of a solution. There it is there, and it's 0.0195. I'm not going to go through all of that, just assume that you can do these things. And then when you do the limiting thing, you need to look at the chlorine reacting with 2 KBr, because there's the equation with the balancing in it. And there's the number of moles that are calculated in both of those. Now with the balancing number, I'm going to go with the KBr. Remember, you can do it for the chlorine or the KBr in this case. I'm just going to go with 1 from now on. I'm going to go with the KBr. 0.0195 moles of KBr would only need half that number of moles of chlorine to get rid of it completely, to react with it completely, which is 0.00975. You have got 0.01826, which is bigger than the actual number of moles that you need. So the chlorine is in excess. There's more chlorine than could react with the KBr in this question. So therefore the KBr is going to run out. It is the limiting chemical. There we are. The question was simply which is the limiting reagent. When you go on to that, past that, what then happens is when you've got a limiting reagent, how much of a particular product can you make? So we'll do that. See you in a moment. So here's an example where you've got a reaction where we're now going to go, we've got 2 chemicals, one of them will be in excess, the other one will run out because it's the limiting reagent. The limiting reagent will then indicate how much of the product you're capable of making. So we're going to go, this is going on to calculate how much product you get when you've got a limiting reagent. So we've got C4, it says there, what mass of C4H6Br4 would be formed if, and they've got these amounts of C4H6, which is a diene, it's a buta-1,3 diene, and a mass of Br2. The equation is there, takes 2 bromines to react with C4H6, and therefore you get this product. So it's 1 to 2 making 1. So we need to have some kind of comparison. Can't do it with grams, grams isn't the way to do it, it's got to be in moles. So the number of moles of C4H6 is 1.08 grams divided by the formula mass. Formula mass is 48 plus 6, which is 54, comes out to nicely round, nicely, not a whole number, but a nice simple number of 0.02. 5.59 grams of bromine divided by 2 lots of 79.9 is 0.03498. Then you need to decide, okay, where's the limiting reagent in that? Well, I'm going to do bromine because it's nearest to me, and that amount of bromine, 0.03498 moles, would be able to react away half that number of moles, because it's 2 to 1, of the C4H6. So you need to divide that by 2, it's 0.01749 moles of C4H6 is capable of reacting with this amount of bromine. When you look at that, that number is less than that number. So there will be C4H6 left over. So therefore the limiting is why the limiting is pointing at the bromine. So there it is. So we're limited by what we've got with the bromine. So then you've got to decide how many moles of this the limiting in this setup allows you to produce. Now you can do it either way. You can go 1 mole of that makes 1 mole of that. How many moles of that actually did get to react? It's 0.01749. Or you can go, oh, it's 2 to 1, so it would be half the number of moles of bromine. The answer is still 0.01749 each time. So we make 0.01749 moles of product. Doesn't ask you how many moles, it asks you what mass. You need the formula mass of this C4H6Br4, which is 373.6 apparently. And so you multiply that by the number of moles that we calculated there, it comes out at 6.534 grams. No, it doesn't, that's too accurate. Looking back at the setup of the question, 3 significant figures, it's not going to be 4. So we turn that into 3 significant figure answer of 6.53 grams. That's the answer. So that setup, 6.53 grams of this product. End. See you for the next one. So the next stage on is that you work out how much product you would get, but what if there was a percentage yield in the procedure or in the process? So I've set up nothing new. I'm not going to go through a whole new load of calculations. We're just going to go with the same one as we've just done with the C4H6 and the 2 bromines, but now it's doing it with an 88.8% yield. I must say I just plucked that number out of the air. So that's the same equation as we had on the previous example. If you do it at 100% yield, which was the previous example, we got 6.53 grams. Now, we don't get everything that we want. We get other products, we lose some stuff, whatever. That's the yield is 88.8, and there's always a reason why it's not 100. And there is the calculation. So it's 88.8 over 100. You could, if you're okay with percentages of mass, just go times 0 point percentage. So 0 point and then write the digits for the percentage. Either way it's the same. And it comes out as 5.8 grams of C4H6Br4. So that includes a yield reduction of the amount of product that you get, as well as the effect of having a limiting reagent. We just got one more example and then we're done. Like I say, there's some follow-up questions and I'll see you. Are you making notes, by the way? Are you stopping and starting and writing stuff down? You know you should. See you in a moment. Now, you can tell by the amount written on the board, this is a little bit more complicated. So, 2 things you're going to have to do in this question, because there's A and B here. Got a reaction there between ethane and oxygen. Often you see the combustion equation for 1 mole of organic, and then it'll have 3.5 in the case of this, but I want to do it with some awkward numbers, so I've gone for the full whole number version there. 450 cubic centimetre of ethane in a container and 1650 centimetre cubed of oxygen put in there with it, which is 2,100 altogether. And you use a spark to get the reaction started, so you mix it, you put them all in, spark it, there'll be 2 little electrodes go in, spark, and the whole thing reacts. And the 2 questions are, what volume of a reactant is left over? So that means when you work out the limiting reagent, the one that's in excess, how much is left over of that excess reagent? What will be the volume change once back at original conditions? So we're going to use Avogadro's law in this because we're talking just about reacting volumes together. So there's no condition change back to the original conditions, or whatever the temperature and pressure were. It doesn't matter what the temperature and pressure were, providing you go back to exactly that. Then Avogadro's law works. You change the temperature or the pressure, or both, Avogadro's law doesn't work. You need PV equals nRT. So, 450, 1650. Got to do things with the balancing numbers. Balancing numbers are 2, 7, 4. Now the water plays no role. I mean, technically it has a little volume, but we're not going to get excited about it because it's a liquid. Now, 450 cubic centimetres of apparently C2H5. That's a little bit weird. Let's try C2H6. That'll be a little bit more like what it's supposed to be. 450 cubic centimetres of C2H6. how much oxygen would we need? Well, if you had 450 of that, it would need two of them require 7, so it's 7 divided by 2, 3.5 times more, because the balancing number could be 3.5. So 450 times 7 over 2, it needs 1475 cubic centimetres of oxygen. You've got more than that of oxygen, so the oxygen is the excess because the limit is on the ethane. I might have said ethene, no, it's ethane. So there's an excess of oxygen of 75 because the limiting reagent is the ethane, so the oxygen won't all get used up. 75 cubic centimetres more oxygen put in than you would have needed for complete combustion. And then the second one is what's the volume change. Now there is a kind of proviso on that. The reality is that most containers are hard-walled containers, and so this question is not valid. I'll come to that just at the end. So initial volume, which is the amount of oxygen and ethane that went in together, is 2,100, which I mentioned earlier. It's the two volumes added together. The final volume of the carbon dioxide, it's only carbon dioxide that takes up the space in the products, because like I said, the water doesn't really come in, don't take up very much space, but the conditions I'm working at is a liquid. So this time the balancing numbers are 4 over 2. So 4 product, 2 reactant. 450 times 4 over 2 is 900. So we get 900 cubic centimetres of carbon dioxide. There's also 75 cubic centimetres of the unreacted oxygen sitting around in there. So 2,100, if it all went, you'd have 0, and then we get 900 back and another 75 back for the oxygen. So we take those away, we get 1,125 cubic centimetres. It's reduced by 1,125 down to 975. So there's the final volume is 975. Now here's the little proviso thing. In a hard-wall container that wouldn't happen. You need a container, in order to get 975, the container has to be flexible and be able to change volume. You couldn't do this in a balloon, it would set fire to the balloon material. You could do it in a glass syringe, but it might cause a bit of a problem with a big glass syringe. So in reality the question in practical terms is actually going to be what will be the pressure change. But we're not going to get into PP equals nRT, but you could then go, calculate what the pressure would be in there, because the volume of the container is fixed at 2,100. But we're not going to do that because that just makes limiting reagents more complicated than it already is. So there's a bit there, you might want to pause it and have a write of that. Now there are some more questions that follow this up. They'll be, next to the video in the downloadable link, or you might get them another way if I teach you. And if you're still struggling with moles, I have a book about moles, book 1, moles for A-level chemistry, lots of facets of that in there. Do some practice with the book. Oh, you might have to buy it, it's £7.99, it would be a delight if you had it. I will see you soon, because there's more of these to go. Bye.